left off at this point, where we did an example with a parabola. I'm going to quickly reiterate it so we're all clear on this. Again, quickly reiterate. First, if the focus is at -2, 0, here's our focus, or our focal point. Okay, that's our focus. Now, if I keep going further back, at -4, see x equals -4 here, I'm going to put my directrix. Now, we already did this one yesterday. How do I know again that it's a dashed vertical line? Why isn't it horizontal? Like y equals -4 versus x equals -4. What's the real difference there? You can think of it like the asymptote. Good, Derek. Remember the vertical asymptotes? Their equations were x equals some number and x equals some other number. Now, with that in mind, take a look at this one. You have x equals -4, which makes you think of the vertical asymptotes. Now, when we had vertical asymptotes, they were simply vertical dashed lines. So you can think of your directrix like that. That's fine. Now, if this had said y equals 7, somebody describe to me what that would look like. Y equals 7. Why this way?
Because it's like y and it's like going up the y-axis.
Perfect. Or not on the y-axis, but on the same y number. So what Juliet is saying is y equals 7 is a bunch of dots up at y equals 7. Because like this point here would be 1, 7, 2, 7, 3, 7, 4, 7. Is the 7 changing? No. So we call this a constant function again. Okay, remember, the horizontal line, this is a side note, like y equals 7, we call a constant function. Whenever a function does not change, it's called a constant function. Constant function. You're going to hear that term in pre-calc. You're going to see it when you go to calc. Okay, both of those. Now another term they might call it is static. Anybody ever heard the term static versus dynamic? Just wrong. Static versus, yes, not wrong there.
Static means you're not moving.
Good. Static means not moving. Very good. Or not changing. Whereas something that's dynamic, what are they? Yeah, they're always changing. They're always moving around. They're always moving around and saying different things. So dynamic is something that is constantly changing. So in college, when we study engineering, if you choose, we study math and science, you might even take a course. So the topic in engineering that's to me, the most interesting topic of all is called dynamics. Because you're studying bodies that are in motion. So you start by looking at like all of Kepler's laws, you look at planetary motion, and you take that macro level, and then you start looking at things on Earth. So then you look at like a box and how its motion works. Why does it rotate if you push it hard enough? When will it slide? When will it not slide? Like these are all the questions that you answer in these classes. In statics is when things aren't moving. So statics, for example, is like, well, for example, what about this wall right here? There's some sort of a load that's bearing on one of these columns in the wall. Where are those columns located? How far apart? What are their dimensions? That's statics. Like civil engineering, Mr. Smith studied statics a lot. Things that are not moving. Bridges. Bridges really shouldn't move. I mean, they have room for flexibility and some sort of deviation. So believe it or not, a bridge can actually like wobble, or not wobble, but wave a little bit. You've seen the Tacoma Narrows video sometimes people talk about where the bridge started to really start to move back and forth and then it just started to, have you seen this before? No. Break. It starts breaking and then it collapses and all the cars fall in. It's a very famous video. Type in with a C though, Tacoma. Tacoma with a C. I'll put a link on that.
It's wobbling all the cars slowing.
It starts to vibrate, but then it reaches its natural frequency, which causes it to then separate. It's a technical term, but all it means is that it reaches a level of vibration that it can no longer withstand. Okay? But bridges are meant to vibrate. They are meant to move. That's why you notice every 100 feet on a bridge, you're going to see like a metal plate that actually connects two other pieces. So you're taking these chunks of concrete and you're connecting them as little piecewise functions. Imagine if I had a bunch of functions on a graph. The first one looked like that, and the second function looked like that, and the third like that, and then like this. Don't they make a bridge really? That's what's going on a bridge. There's these connection points here. You might even call them nodes. There's a term to use, nodes. These connection points allow for the bridge to deviate, for the bridge to start to, maybe alter its height by a centimeter or so. But when that starts to become uncontrolled, like the Conics Narrows Bridge, that bridge started to really go crazy. It started to break and stuff. Bricks started coming off, the concrete was splitting. So it's crazy. Miguel had a question first, then we'll come over to Julia.
Talking about dynamics. Is that same math applied to those commercials that you see on YouTube about Nike when they start analyzing the person's movements and all that and ability.
And you're absolutely right. Absolutely. You're talking about the stuff like Nike Fit that they've come out with, where you can put the tracker in your shoe, or you can put it on like your wrist and stuff. Yeah. And now they have stuff. Is there a newer one that tracks your whole body, or just your general motion?
Yeah, I watched this Nike training thing over the summer.
Okay.
Right. It was like 2 months ago, and it was like they test everything, your speed, your walk, all that.
So all that stuff is exactly what you're thinking about. So dynamics is studying things that are moving. So they're using all the equations from dynamics to take what they see and piece it together. We're able to look at somebody moving and give a result that takes, imagery and converts it to math or numerical values. That's what the computer is doing. So there are computer engineers that are there that are writing the software code that do that. Then you have electrical engineers that are programming, that are using the lasers that are in there, or the little sensors to notice your motion. There's mechanical engineers that come up with the ideas and how to actually work it. Mechanical engineers are usually the people that invent the stuff or come up with the general scheme. Not much civil engineering, mechanical. There's not much civil engineering, not much chemical engineering. Maybe some chemical if there's chemicals involved in the machinery, but I doubt it. It's probably just electrical. So it's electrical engineers, mechanical engineers, and computer engineers that would be involved in making that object or that device. Julia.
The bridge that you're talking about, like the video, is it really old?
Yes, it's like in black and white. The bridge starts to like oscillate back and forth. The wind caused the bridge to vibrate at a certain frequency, which eventually caused it to go into what's called like an uncontrolled state. Its behavior became unbalanced. It's always a combination of things, for sure. Like the wind itself is not just going to cause it. The temperature, the humidity, all that stuff plays a role. But generally speaking, it was the wind that made it. There's a lot of articles about it. Right. To answer this question, though, that was a bit of a side note. There's a bit of a side note. Now, you've got a focal point here at x equals -2. You've got the directrix at x equals -4. Therefore, the vertex, as we said, which is equidistant from these two, must be the midpoint. Again, the vertex is equidistant from the directrix and the focus, always, 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 when you're looking at a parabola. Okay? So again, there's your vertex at x there. How do I know that that's equidistant? Yeah, it's one from each side. Or, remember from geometry last year, how do you find the midpoint between 2 points?
You add them and divide them.
Good memory, miss. Well done. Nobody in the other classes remembered yesterday. I asked that question in the later classes. I didn't ask it yesterday. So remember, if you want to find the midpoint, it's x1 plus x2 over 2, y1 plus y2 over 2. That's always your midpoint formula from geometry last year. What do we call those when you add two things divided by 2? The average. So really, what are you doing? The midpoint is just x bar comma y bar. Remember we introduced x bar as average the other day? X bar comma y bar. It's just the average. And if you think logically, this is -2, 0. This point, even though I know it's not a point, we're looking at this location right here, though, is -4, 0. What's the average of 0 and 0?
0.
So the y value doesn't matter, really. And it's obvious, because it's a linear thing, right? We don't have any delta y in this picture here. We only have a delta x. So the delta x is just going to be back by 2. Okay? Back by 2. But if I were to add these numbers together, what do I get? -6 divided by 2 gives me the -3 right there. Okay, again, the midpoint is really okay, there's our midpoint. So again, the halfway point between the two other points there. Please, guys, please quiet so people can listen. And if you have comments to contribute, obviously they're always welcome. So this is our midpoint here. This is our midpoint here. All right, the next example we're going to look at now has to do with an ellipse. Remember, just to review again, what are the 4 types of conic sections from yesterday? Come on.
Circle,
Good. Parabola and hyperbola are very similar, and their names are similar. They both end in bola, right? B-O-L-A. Now, both of those look similar. The parabola is this. Remember, the hyperbola is simply adding down or having another piece of it at the bottom. Or a hyperbola could look like this, okay? Or then a parabola could just be like this also. Now, a circle is this, right? What's the ellipse really? What do you do with your hands? Just stretch it. Good. Just stretch it. Okay? That's all you're doing. So it's just like circle, oval. And remember, when you have a circle, how many points do you have in the middle?
One.
But when you have a ellipse,
2.
Good. You have 2, and they're called focal points. Good. Plural. What's the term focal points, though?
Foci.
Foci or foci. Right? Let's try to say it right. It was funny because I always said foci, and last night I was looking at a video to put online for you guys. And somebody said foci. So I'm not sure which one it is. I've always said foci, and my teachers have always said that. I know that, but it could be foci. I don't know.
Maybe the person had an accent.
Maybe. It's possible. Actually, one of the videos I did put up last night was Conics sections in everyday life. It's a little like 6-minute video, and the narrator has a heavy accent. I can't figure out where they're from. I think they're from Spain or a Spanish-speaking country because the accent sounds Spanish, but I don't know if it's Europe or if it's like a Central American country. It's like 7 minutes. I put it on Netline. Just click on it.
You changed the little chicks photo. That was funny. Shout out to my peeps.
So that one? Did anybody not see that, by the way?
I saw it.
On Easter, I put a little picture that said shout out to all my peeps.
Oh yeah.
Remember the peeps saying it?
Yeah.
I thought it was funny. I did put it in one. I put it with baseball season.
I know.
Baseball season together.
Yeah.
Put a sandlot picture.
I'll probably change it in a little while, but I just, baseball season doesn't begin. Do you have a question?
They come with an old
Don boxes and
Okay. Now, the problem begins by telling us we have a vertical major axis. When you have a vertical major axis, first of all, major versus minor from last year, we did arc lengths. If you had a circle, the arc length between the 2 points that is shorter, we call the minor arc, and we call it the other way around the major arc. Same idea. The major is the bigger axis. The minor is the smaller axis. So I want somebody to come up and draw what this ellipse is going to look like generally. Just from the first sentence alone. What would this ellipse look like? We don't have any idea here. Or you want to draw it on your paper and I can...
Can I try? I think I'm wrong.
That's all right. So again, just based on the first sentence, don't even think about the rest. Just based on the first sentence, what kind of an ellipse would we have? What would the general shape be? Well done, miss. Well done. Because again, it says there's a vertical major axis. This is your major axis right here. This is your minor axis right here. Again, red is major, blue is minor here. So because it said vertical major axis, Julia thinks vertical is up and down, so let me put the longer axis up and down. If it said vertical or horizontal major axis or a vertical minor axis, it would have been the other type of ellipse, a horizontal ellipse. All right, now let's take a look at what it says. One focus is at 0, 3. One covertex, remember covertex from yesterday, is at 1, 0. So let's draw an XY plane now. 0, 3. Up, down, left or right? Up. Very good. Oh, you're just repeating me there, sorry. Question was up, down, left or right? Where is 0, 3 located?
Right.
Up, be careful there. Right is 3, 0. Okay, you gotta be careful. There's a lot of zeros that are gonna show up in this problem, okay? Again, X first, you don't move anywhere, then Y is up 3. A covertex at 1, 0, that's to the right now. Okay, that's to the right now. All right, let's think about this for a second. We've got a focus at 0, 3. We've got a covertex at 1, 0. What do we know about an ellipse? What do we know about an ellipse?
It has two focal points.
It has 2 focal points. It has like 2 lines in it also, Jay. Good. What else? It's an oval. Good.
Oh, isn't like it's the 2 points start about to meet? The center point of the circle.
That becomes a circle. Very good. As the 2 foci become closer, it becomes a circle.
Then we get the galaxy.
Juliet?
Isn't it there's two, apart from the two folks, there's two distance that is like,
Okay, good. So, using that knowledge, Juliet, this was called a co-vertex, right?
yeah.
What else can I gain from that information? I can do something else with that point right there. If you have any suggestions, what? Reflect. Why reflect it? So what do we call that? The ellipse has symmetry. The ellipse is symmetric. That's the key there. Okay, again, these shapes that we're looking at have symmetry in them. A lot of symmetry. The parabola has an axis of symmetry. A circle has an infinite amount of symmetry lines. Think about it for a second. Any diameter is a symmetry point, right? Or a symmetry line. So there's infinite amounts. A ellipse has two types of symmetry. One along the major axis, one along the minor axis. A hyperbola from yesterday was this shape. I mean, it's so obvious that there's symmetry right there, right down the middle. Okay, so these shapes have symmetry. Now, when you take pre-calculus, you're going to use the idea of symmetry a lot. You're going to study things like odd and even functions, which exhibit properties of symmetry. An even function exhibits symmetry about the y-axis, like a parabola that's opening upward, or a parabola that's opening downward. That is symmetric on both sides. That's an even function. An odd function exhibits symmetry through the origin, which means that if you think about a cubic function, you see this shape here, and then it turns into this shape, right? Isn't there symmetry? But it's not very obvious, because if you take this one here, this portion here that I'm highlighting green, and rotate it 180 degrees, don't you become that?
Mm-hmm.
There's the symmetry. That's called symmetry through the origin. So we're not going to touch too much on that this year, but next year, if we count, you're going to talk about odd and even functions, and functions that are neither odd nor even. Neither odd nor even also. Okay? The best example of an odd function is y equals x cubed because of the odd exponent. The best example of an even function is y equals x squared because you see an even exponent there. But those are just very basic examples. What if you have something where it's x to the fourth, but then plus an x to the third? What happens then, right? Okay, so that makes x. Say again?
Isn't it still going to be x?
It should be a little bit different there because you have an odd and even together, which is going to cause some disagreements between them. You're not going to have either in that case, in that specific case. Okay, so it depends on when you plug into the function, is it symmetric on both sides? If it is, then it's going to be even. If you're plugging in data in the function, you get symmetry about the origin, then you know it's an odd function. Okay, so keep that in mind when you do these. So again, as Luis just said, we have symmetry. So let's take our co-vertex and put it over here. Now it's very tempting just to put my other focal point down and finish off the ellipse. Because if I see a focal point up at 3, and I know that this must be my minor axis here, why do I know that that must be the minor axis?
One of them.
This is between the 2 points when the x-axis.
Hold on. The distance between the co-vertices, or the distance between these 2 points along the x-axis. So, if this is up 3, right? See that? What must this be?
Down 3.
Down 3. There's my other focal point. So I've got 2 focal points, and I've got 2 co-vertices. 2 co-vertices. Now, go back to your shape of an ellipse. Where were the focal points located? In the middle. In the middle. So, they're not the ends, are they?
No.
But the co-vertices, B and negative B, those are the ends, aren't they? So what I need to now think about are several things. First of all, is there any way that I can determine what's the missing distance here at the end, to see how much of a gap there is? That's the first thing I have to think about. You see what I'm saying by saying that right now? Because we have the focal points. We have these 2 points right here, here, and here. If I want to figure out, well, what is that missing distance, so I know how far down or how far up I'm going to go? Is there any way that I can do this? Again, I'll go back to this diagram if it helps. I want to figure out this distance and this distance. How can I figure them out? That's the starting point. We can start by saying, yes, D1 plus D2 equals 2A. This is interesting what we're going to do here. D1 plus D2 equals 2A. That is absolutely right. Trayvon?
There are two different equations, but they're two.
We're going to need other equations for sure to do a problem like this, exactly. Again, we're going to definitely need other equations to do a problem. Now remember, this is like you're flattening out this rope here. Remember this distance here is really 2a, it's like you're flattening out the rope. If you took the two focal points and just pulled them taut, they would flatten out to that right there. So all we really have is d1 plus d2 equals 2a right now.
Then can't you subtract like the line you already, like the amount you already have,
The foci?
Yeah.
The foci?
Yeah, d1 plus d2, and they have like 2a, you can subtract what you already have.
We could say 2a minus 2c equals x, and we're looking for x, or 2x, right? Because 2a would be this full distance here. 2c would be that distance there. When we subtract this distance minus this distance, we get two of these little pieces, which we can call x and x. That's one way, but the problem is this, guys. For this kind of a setup, you have too many equations, too many unknowns right now. So without more information such as eccentricity, meaning how flat or how bulging the ellipse is, there's no way we can actually determine the other endpoints. So for now, we're going to just sketch an ellipse. Okay, but I wanted to show you that right now. We can't do that just yet. We need more information than what we just have right there. So let's go ahead and just sketch an ellipse. We don't know how far high up it's going to go, but if it goes that far up, you got to make sure it's symmetric at the bottom. Okay, again, I went up 1 and about 2 units, so at the bottom I went down 1 or 2 units there, just to show the symmetry. Okay, just to show the symmetry. Any questions on that one? I know it's not easy right away, but we got to be sure that we're understanding what's going on there. Okay. Let's take a look at an example of a hyperbola now. Well, you know what? Let's do a circle real quick, just because a circle is so simple. You know what we're going to do actually is this. Because this concept is taking 2 days, I'm going to push the test back another day. I thought about it last night because it's going to take a full day today. Okay? It's not really going to hurt you. It'll just help you guys, actually. So what we're going to do really, what we're really going to do is, today I'm going to mainly go into concept 65 only. This was the original plan here, but it's not going to work too well. I'm going to do 65 only. Tomorrow I'm going to skip to 67, then go back to 66. Okay, I know it sounds weird, but I realized after ordering them that it might be good to switch the order. But I didn't want to screw up your books outline sheet there. Hooke's Law. Hooke's Law. Springs. That's what springs are. It's like the most governing law in the world. Hooke's Law. Or one of. So, we got a circle. The circle at the center. The center is -1, 2. So I go -1, 2. There's the center. Now, you know how to do this because we did it last year. No matter what teacher you had, you graph circles for sure. So, how do you graph the circle? What are our steps here? What are our steps?
Radius.
Okay, look at the radius. Tuesday. Okay, relax, guys. Everyone's so angry at each other. I hope not. He's a nice guy. Now, I want to do what? Sketch how many points? What do we say?
2 points.
On
both sides.
Good. So how many altogether?
4.
Thank you. So my radius is 2. So I go ahead, I start at the center, and I go over 2 units, and I put a dot right there. So that's one of my radii. Then I go back to the center, I go down, I put a dot there. I go left, I put a dot there, and I go up, and I put a dot there. And I don't need to put the radius in every time. I was putting the radius in once. So in case you want to label that as R, it might be useful in your notes. And then what do I do with those 4 points? Connect them how, though? Good. Don't connect them like a diamond. This is not a bunch of linear functions. You want to connect it, watch, ready? Just do one at a time. Make a quarter circle here. Make a quarter circle here. Focus on a quarter circle 4 times. It's so much easier. Take here, watch. Quarter circle. Only focus on the quarter circle. And they'll come together, actually. Up here, another quarter circle. You get a pretty good shape.
Are you actually like dotting it?
Did you make it look like you're just going straight down?
Watch.
Now I can hear.
I mean, there's a little function on there, Jason, but it's not that hard to do. You can do that. It's not behind you. That's not hard to do. So we got a circle. Now, let's make some notes about the circle. Let's make some notes about it. First, its center is not at the origin, right? It's been shifted. What are the shifts on this circle?
Left 1, up 2.
Very good. Left 1 and up 2. Left 1 and up 2.
He's been doing this for like 30 years, guys. Come on.
30 years. 3 years.
Oh.
Left 1 and up 2. Now, keep that in mind because when we start doing graphing of circles, when we start graphing circles, okay, on Thursday we're going to do graphing circles. We're going to use that terminology. One other thing. What's another characteristic of this graph that you don't always see? All circles should be perfect circles. What's the characteristic of this graph? All circles are symmetrical.
Triangle.
It goes into a different quadrant.
The triangle.
Okay, it's in 2 quadrants. Good. It's in 2 quadrants. That's fine. The radius, the right angle. Which right angle? I mean, there's a lot of right angles. That's why. Remember? Say again. They're equidistant. All those points are short. This is the right angle that's important. Why is that the right angle that's important? What happens when a right angle meets a line? What happens when a radius meets a line and there's a right angle? What do you know about that line? What must it be? What is it? Tangent. Very good. Tangent. This is a point of tangency right here. Whenever a radius intersects or meets another line at a right angle, okay, and that line somehow touches the circle, it's going to be a tangent, always. That was one of our laws from geometry last year. So this is a point of tangency, or a tangent point. Are we all clear on that? Again, these are important things that I'm adding in. Little things to note. Why am I adding these things in? Because 2 reasons. 1, they're good to know. It's good prior knowledge to think back upon. You can use your knowledge from geometry. 2, these are the kind of questions that you're going to need to be able to answer, at the minimum, to do well in classes like pre-calculus and calculus. So I'm reminding you of these things because when you get to those classes, they're going to pull all your data and all your information together. They're going to pull not just like Algebra 2 and geometry, but Algebra 1, arithmetic, a little bit of statistics here and there, very minor statistics and calculus, if any. Okay, they'll use things like deviation and stuff. Very basic. But again, you're taking all the knowledge you have in math and putting it into one subject. That's why it's such a, what's the word? Developed topic. Okay? Because we use so much information all to answer one simple question sometimes. All right, let's go to the next example. We did a hyperbola already to look at. Okay, let's look at the example of it now. So I begin by drawing my XY axis. Let me just really quickly look at something before I say anything. Okay. I think I called, see the word I used, the center at the origin? See that there?
So it's like,
I called it the vertex in our notes.
it's the same thing.
Okay, I'm going to put in parentheses so we're clear on that. The vertex and the center of it, hyperbola are the same. Yeah. All right, sorry about that. Now, the center is at the origin, so here we know that's going to be our center. Slant asymptotes at y equals plus or minus x. What does that plus or minus mean again?
It'd be,
Positive or negative?
Good, so I have 2 graphs or 2 asymptotes to graph here. Remember, slant asymptotes look like this, don't they? And y equals x looks like this. And y equals negative x looks like this. Okay, that's why I have to do 2 of these. So I start by putting in my asymptotes. And I should actually be doing that dashed. Here, Jason, I'll show you the one on here. Take a look. They actually have dashed lines on here. So you can go like this and just run it off, and it actually comes out dashed. Isn't that kind of cool? Come on. It's a little bit cool.
Maybe it's not coming.
Yours are better.
It's too perfect, isn't it?
This is the kid that's the. Oh, use a blue line.
You can make any color line, really. You can change it.
Miss Jenkins can't do that.
Sure she can. She doesn't know. Jason, watch. You go over here, you open the gallery, or the color toolbar right here. You pick one of these colors, say this purple one. And we pick a new color. What color we want? Orange? Like that one right there?
Magenta.
I'll try orange. Yeah, white. Save tool properties, and now look at my line. The line is now orange. Okay? The next thing we want to do, it tells us one vertex. Oh, wait, hold on a second. Okay, sorry. In your notes yesterday, let me go back and recorrect what I just corrected. I was misconstrued on what I put here or what we saw here. That was given as your vertex right here, sorry. That was given as your vertex. There's your other vertex, which makes sense. It's like the vertex on a parabola, okay? So, please recorrect what I just corrected. Okay, we call that the vertex. So again, these two dots here, these oranges were vertex. This here was the center. Okay? Now, back to this. We have a vertex located at 0, 2. Where is 0, 2? Up 2. Here's one of my vertexes, or vertices. Where?
0, -2.
Very good, because of the...
Negative plus negative.
No. Because of the symmetry, or the axis is fine, but the symmetry here. It is an axis you're going about. Because of the symmetry here, if you have one point above the slant, think about this, guys. What did asymptote mean again? What did it mean? Mathematically. People.
Oh,
No, your
it's
test
the
too.
point in the graph where the line can't go.
Thank you, very good. It approaches that line, but it can't hit or intersect it. So, here's what's going on right now. If this is a vertex, it's got to have some sort of a cup shape there, right? Now, it's going to go off, and it's never going to touch that line, though. This one's going to go off, but it's never going to touch. So where's the other half? As Brandon and Juliet said, down on the other side. So I go down 2 now, put a point, and there's that half, and there's that half. So the blue curved part is the important part here. Okay, the dashed lines are your asymptotes. They only help you draw the graph. They're not actually part of the function. Again, asymptotes don't really exist. They're not actually part of the function.
Are you slick?
Juliet.
Okay, so the lines are
Okay. Glad to. Now, after that, let's go on to the next thing we're going to look at. I'll tell you what you need to write. Hold on for a sec. There's no more.
Oh, dude, no, cool, not cool, man.
What is
Oh,
He's an overall.
So here's what you want to be writing down. All conic sections, we haven't looked at any equations, and we're only going to look at equations of a circle, really. There's an ellipse, a hyperbola, and a parabola. We can look at equations of them. Okay, but you're going to study more of those and recalculate when you need it. Not me. Now, the general form here, the general form is given on the board, and this is the general form for all conic sections. Now, sometimes you won't have a d value. For example, like d will be 0, so you won't have that term there. Or you might not have, a b value. That'll be 0, so that'll drop off. But if you keep it in the standard form, we can look at what's called the discriminant again, but the discriminant of this equation now, of this equation. And this will tell us what type of a shape we have. Okay? Remember the discriminant we looked at? If b squared minus 4ac was greater than 0, we had a real number. If it was equal to 0, we had a repeated root. If it was less than 0, we had an imaginary root. Those are all the types of discriminants. There were 3 types. The 4th type was a special case. Same thing again today. We're looking at b squared minus 4ac as our discriminant, which is what you want to write down there, and we're going to use this data table. If b squared minus 4ac is less than 0, it's an ellipse. So ellipse is like the imaginary root. Okay? I would really write the general form in the box, those two things. Okay? By the way, guys, let's make sure we note this. The only things that can actually be 0 are these three. The hypothetical before, I said B. Only these last three can actually drop off. Okay? Only those last three.
A can be 0, right?
A, B, and C cannot be 0. So the other ones are the only ones that could drop off. Okay? The only ones that could.
So you also want to start with B squared minus 4 and C.
Yes, because that's the discriminant. That's what we're looking at. Now, next part. If the discriminant is less than 0 and A is equal to C, and B is equal to 0, we have a circle. So remember, if it's less than 0, it's either an ellipse or a circle. But there's a special case in an ellipse when A is equal to C and B is equal to 0. Okay? This is an and statement there. All those properties need to be exhibited. You must have a negative discriminant and A equals C and B has to equal 0. Why did we put this here? Guys, for a second, do me a favor, don't write this down. I'm going to come back to you on it tomorrow. Okay? All right, just erase it for a second. Only because, look, what did we just say? When B is equal to 0 is when we have a circle, right? But this says that A, B, and C can't be 0. I got to ask Mr. Smith to find out. Okay?
No, lady plays Libya still.
I'm trying to think why. Mr. Malinchik helped me with these notes, and I know he made this part, but I'm trying to think why it would say A, B, and C can't be 0 there.
Wait, you guys help each other do notes?
We both teach Algebra 2. He teaches Honors Algebra 2 to the sophomore group.
Why couldn't they do that when I was in freshman?
We had this discussion last year. Trust me, I agree. There's no point writing this little note there.
That's why you have to study outside of school. Beat those jobs. I know, right?
Some of them are, yeah. And what we need, you're going to get exams. It's either statistics or calculus. It depends on the grade. Right now, they're
already like points ahead.
you need a high grade.
I know Slizzy
It takes a lot of work.
What?
It's very high grade pre-calc to be able to take calculus. And she was asking about some students that are in your grade, like they're low on. So right now, I don't think anybody's on calculus. Now, the third one. We gotta keep going, Jay. Yeah, today. The third one. When b squared minus 4ac is equal to 0, when the discriminant equals 0, you have a parabola. In the fourth case, when it's greater than 0 or positive, you have a hyperbola. Okay? We're gonna have 4 cases here today. That's all. So all we're gonna do in the next few examples is just go through some examples of classification. Is that clear? We're gonna be given a form. We're gonna have to classify it. That's it. This should be a very easy topic. Okay? This next part here. So we go to our equation here. It's got to be in standard form first. Let's take a look at this one here. According to our standard form that we had, the thing next to x squared is a. So let's call that a there, the 3. Whatever's next to xy is b. Whatever's next to y squared is c. Then the constant at the end is f. So take a look at this function here. What's missing? What's missing? D and E. Where are they?
There's 0.
Good, there's 0. The value of D and E are really 0. That's why they're not there. Okay, D and E are really 0. Please remember that. They're not 1. It's a common mistake. People say they're 1. So let's do b squared minus 4ac. We got 2 squared minus 4 times a times c. What must it be? I'm not even going to do it. Don't even do it, please. Don't do the problem here. It's a negative negative, which makes it a
Positive.
So you're going to be adding 2 numbers. You must get a
Positive.
positive. So the answer is positive. Who cares? Once it's positive, what is it? Which one? Which one is it once it's positive?
It's like a U.
It's a W. What was that one called? Hyperbola. Not W, but double U. Hyperbola. Hyperbola. I don't know. She did. Okay, hyperbola. Because I go back to my table and I see when b squared minus 4ac was greater than 0, this indicated to me that there's really a hyperbola on the graph. So since this number is going to be positive and then minus a negative, you're just going to be adding two positive numbers, which must be positive. I don't care about its value. Think about that logically, right? It's really important that you get what I'm saying now, because you're going to use this again. You're going to use this topic right now that I'm telling you, where I don't care what the number is. It helps you a lot later on. Again, just remember, a positive and then minus a negative is really adding another positive. When you add two positives, it's still positive. If you added two negatives, it would still be negative. If it's a negative and a positive, then we have to figure out which one is bigger. Okay? Again, though, it doesn't really matter right now. That's it. That's all we're doing for this one. Number 6. For this one, what should I do to the equation? Rewrite it. Why? Good, Andrew. It's not in our standard general form here. So, let's go ahead and rewrite this one. First, what goes in the very front? Good, the x squared term. What comes after that? xy, but is it there?
No.
So b is 0. So remember that condition we were on earlier, a, b, and c can't be 0? Definitely cross it out. Okay? Next, what's the c value going to be? What's the next value? Y squared. So we got a equals -1, c equals 1. Do I have to go any further?
No.
Why not?
Are you fine with those negatives?
And 0.
Okay. But I have everything I need, right, for the discriminant? What's the discriminant? B squared minus 4ac. So it's just simply 0 squared minus 4ac. Now, what are we going to get here?
Positive.
Positive. So what kind of a shape do I have? Hyperbola. Okay? Hyperbola. Let's see. I want to do one example with a circle versus an ellipse. All right. I'm going to add one in here. Add one in before we end. Let's take a look at this one now. For this problem here, what do you notice about every number? What is it, Isabel? They're all even. So technically, what could I do with this kind of a problem? Factor or divide everything by 2. Divide both sides of the equation by 2. Dividing this side by 2, I'm just going to reduce everything by 2. Just to make the problem easier on me. I don't have to worry about the larger coefficients anymore. And 0 divided by 2 is still going to be 0. That's why we can do that. So again, I divide both sides by 2. Now b squared minus 4ac. What's b squared going to be?
2x.
Or just,
2x.
sorry, 1 squared, 1 squared. What the heck?
What's that keyboard? What's that keyboard? What did you say?
1.
B squared is 1 squared minus 4ac. What do we get here? What kind of a number? Negative. Why, Victoria? Yeah, it's a 1, isn't it? It's going to be 1 minus some value that's multiplying by 4. Doesn't matter what that number is, right? It's going to be bigger than 1, though. So when I subtract it from 1, it's going to be negative. So 1 minus some value, that's going to be a negative there. If it's negative, we go back to our chart and look. When it's negative, it's either an ellipse or a circle. Which one is it?
I think it's
It's circle.
Oh, it's an ellipse.
It's a circle.
It's a circle.
Tangent.
Because A and C are equal.
Okay, A and C are equal, so you want to say circle, don't you? But is B 0? It's an and statement. You know, I'm glad you guys are going back and forth. This is good, because I like to hear both points. Okay, again, when A and C are equal, I thought it was circle right away too, Derek. But then I said, and B has to be 0. And in our problem we just did, B was not 0. B was actually a 1 there. Okay? B was a 1. So again,
Wait, B is.
A was 2, B was 1, C was 2. A and C are equivalent, but B is not going to be 0. Jason, relax. A and C are 2, and B is going to be 1.
So wait, we have the one from the 1x, 1x bar.
The 1 is right here, yes. There's really a 1 in front of here, because there was a 2 before, now there's a 1. Alright, so here's what I want you guys to do. You have a few minutes, and I really, really want you to do this. Don't just sit there, please. Because it's not, as easy as you would think. Okay, it's pretty much the same thing we did in class, but I have a feeling, and I know I asked Mr. Melichuk, this caused a little bit of trouble with some of his classes. What you're doing in the beginning is simply looking at the characteristics given about the graph. Okay? You're going to be given that actually they're ahead and they're behind and they're opposite work days. So now we're back ahead. And they were ahead where I think the other day. So it depends, but we also have done.
Sophomores are kind of.
We have characteristics of a circle, an ellipse, a parabola. Relax, Jason. And I have to do 2 sheets. The double-sided isn't working. And then a hyperbola. After that, after you draw 4 sketches, I'm going to go down here and look at what we just did. Okay? Determine which shape it is by using the discriminant. Make sure your equation is all on one side so that you're solved the right way. Make sure that it's in standard form before you do this. Okay? Again, please do this now. You have about 8 minutes. Okay, you can probably get the whole thing done actually in 8 minutes. You just sit there and work hard. I really think you could. I have your notes out.
Could you go back to the chart?
Yeah.
Actually, I'll do it.
And Mr. Can you go back to the John, are you done?
Right there.
Really?
Another one coming around. It's 2 sheets because there's only one side, unfortunately, this time.
This is easy.
Yes. It's dangerous.
Did you put make the quadratic thing on the computer?
I did. I put it under like news a while back. You just go under news and searching the history. It'll be there. It will definitely be there. Yeah, it doesn't delete the stuff that's there.
First, I can be real high on that.
Again, guys, if you have a portfolio for me, make sure it's in by tomorrow. It's a really killer 0 out of 30 there. Please get something done. If you want to make up any concepts, please put your name on the board. Make sure you have done the homework already and given it to me before that. I need your homework first.
So what about
I don't want to
You know what I would do too? Like, pencil, because with a pencil you can like write your sketch and sketch around the whole thing, and then draw your name on it. You know what else you could do is just get a compass also. If you want to draw better circles, you have a compass at home? Use one of those.
I don't mind.
How many are here? Awesome. Put your name on the middle one now. Whoops.